Yeah, thanks a lot. Good morning to you all. It's a pleasure to be here. And I especially thank Olga for the, she had some troubles keeping in touch with me because I've been on paternal leave for the last 3 months. So I'm very happy to get all those insights and to get updated here. So thanks also to all of the other speakers and all the discussions we already had during lunchtime and the coffee breaks. Today I want to give you some insights about what we are doing as a team with the Austrian Federal Railways. We've been working hard to implement the big data platform for the last, call it 2-3 years, like really working on it, like every day. The ideas have been there for a long time. Of course, big data is not something that is so new, but it takes a long time to implement it, especially in big sectors like the railway industry. And I'll also show you what we are doing to predict track condition and degradation, and where we are heading in the long term. So just to give you an overview about ÖBB-Infra, so this is just the infrastructural part of the Austrian Federal Railways. We have about 20,000 employees. We have about 4,800 kilometers of network. That is equals to 9,600 kilometers of rails, actually. And we are spending about 2 billion euros a year to maintain our network, but also to improve and to renew our network every year. So just to give you a brief overview, this is Austria. You see the outlines of our network. We have a very heterogeneous geology in Austria. So we have the huge basin areas where you see quite bigger networks. And then, of course, we have the alpine areas where we just have east-western and north-southern corridors, and very different aspects also in maintaining our network. So what we are doing in part of the infrastructural system is, of course, to manage, but also the whole life cycle management. And our responsibility as a team is to provide decision-making tools and data for our track inspectors and our track maintenance teams. So the top priorities in maintenance are safety, of course, then availability and punctuality. So this is, of course, priority number 1 is always safety with the railway. Yeah, how do we do that? So currently we have a team of 7. Actually, starting from yesterday, we are 7. Starting from December, we'll be 8 in the team. And what do we need? We need a lot of data. We need a lot of data to predict track condition and degradation. Where do we get the data from? We have measurement vehicles, actually 2 measurement vehicles in the measuring department. This is the latest one, the EM160, who are gathering, call it 70 to 100 parameters throughout the whole network. They're basically traveling throughout the whole network 1 to 4 times a year. We have usually the track managers are on board, so they can make decisions when there are safety-related concerns. We have a powerful IMU to get coordinates for the data. We have lasers that measure the profiles of the rail. We have a track gauge measurement and a lot of additional services on board. The whole thing, the whole data stream is already managed on board, and the track inspector can have a look directly in real time so that he can make safety-related decisions. I just see. Okay. So these track measurement vehicles have been operating for about 20 years throughout the network and have gathered a lot of data. So every 5 millimeters, we get roughness of the track surface, And then every 25 meters, we get data about the track gauge, so the difference between the two tracks, the rails, super elevation, the quality of the track in longitudinal level alignment, plus for the last 5 years, we have gathered a lot of LiDAR data. So we get LiDAR profiles, which give us a good idea about the surroundings of the tracks. And every 1 meter, we get detailed information about the rail profiles, which you can see here, and the rail profile wear and tear values are being calculated. The measurement vehicles, they travel up to 160 kilometers an hour and up to 250 kilometers an hour, and gather all those parameters on the way. This is our newest addition. We also have a track component video system, which is sitting underneath the carriage. So we get a high resolution picture of the whole track. Also up to a speed of 250 kilometers, you get 1 millimeter of resolution. This is something we are playing around with. For example, this is from the LiDAR data. You can generate something about the trees are being calculated, and then you can see the hazard from those trees along the track. So this was the data we gather ourselves, but then we also have other data sources like ground penetrating radar. I think there's something in the next session as well about GPR. There we gather around 2,000 kilometers. We have ultrasonic eddy current test train measurements from the Hungarian colleagues. And of course, we have a lot of asset data and maintenance data. And all this data is what our track inspectors and track maintenance, track managers need to actually base their decisions on. So currently, what we have in place is this online application, Messtechnik, where our personnel can go online, and then they check after the measurement vehicles have passed. They can check like all the parameters, and our team generates also time series where they can also see whether the track degradation, and they find the spots where they actually need to set measurements. But it's still a manual process, so we just give them the tools to see the data, but they have to do everything themselves. And it's really tiresome. So it's a lot of manual labor to provide the data the way you've seen. And that's actually where the demand for a big data platform arose some years back. It's not so easy within ÖBB because cloud or cloud-based services are not an option because our signaling control is in the same data network as our databases. And we don't want any connections there. So this was for the last years, cloud was always a no-go. So we had to wait and to make the demand that our internal IT provider came up with a big data platform. And it's called the Data Science Hub. So it offers services for storage, analysis, and preparation of data. And it's mainly based on open products, open source products. So the way it's contemplated is we have some on-site hardware. We have a processing layer who distributes the loads throughout the servers. We have an ingest layer where we get the data inside the storage layer. And here we have two databases. Basically, we have a CockroachDB and also Elasticsearch, which you will see a bit later on. And on top, a visualization layer with Kibana and Jupyter, where we have the possibility to deploy R code or Python code that we develop on ourselves. And here we also have the possibility to use our local laptops to access the data, also with R, Python, KNIME, and other tools we use on a daily basis. But to load all this data onto the Data Science Hub, there's one essential thing I think some of you may be aware. You need tidy data. And what we've set up the last 2 years is basically that we try to find a common property set that we put throughout the whole data, regardless where it comes from, whether it's asset data or maintenance data or data from the track measurement vehicles. So all data is combined using the so-called georeference glice nets. It's just a model of our tracks with geographic, topological features. So it's a topological and geographical model. I think we're on a centimeter. It's correct, basically. And it offers possibilities for linear referencing. So all our data are referenced, as you can see here. So every point along a track gets an ID for the model and the additional attribute you need for the linear referencing. We also have the possibilities to do routing, historization, which is very essential, because the lifetimes we look at regarding track is about 35 to 40 years. So we need this proper historization part. So this is something we have set up for the last 2 years, 2.5 years. And a lot of data from our track measurement vehicles is already on the Data Science Hub. So we're talking about, I think, 1 billion data sets with, 150 attributes. Is it big data? I don't know. It's complex data, and it's important to structure the data. Formerly, we didn't have the possibilities to ask a lot of questions we had in mind. And now, by giving the data a common property and having performant tools available, we suddenly start asking completely new questions which we didn't even dare asking or answering. So first thing we came up with was this. So this is an online application which is done in Python and the Plotly or Dash framework. So basically what you see, and I wanted to do an online demo. I'll not do it now, but maybe in the break afterwards you can have a look. So basically you see a map of the whole of Austria. You can see the network, and every square represents a parameter. Here it's the longitudinal level, and every square is the aggregated mean within this geographical region. And already here you can see like high-speed lines, in darker green, which are well-maintained, quite new infrastructure, maybe comparing to here a bit of orangey stretch of track, which is not one of our main lines, basically. So already on this level, you can see the differences within the network. And the nice thing is this thing is dynamic. So what you do, you just zoom in. It will just get more and more detailed. And then you can also add other data. For example, you're interested in GPR, ground penetrating radar data, and looking at the humidity. And then in the background, you see all those bluish boxes which show the humidity also in an aggregated form at this location. And the nice thing is it's not pre-aggregated, so it's being aggregated in real time, so using Elasticsearch. And you can zoom in, zoom in, zoom in until you see each and every value on a 25 centimeter basis. Then you have the possibility to add some GIS layers to get further information. So you see, okay, there's a red stretch here. I can see there's a railway crossing. So yeah, there might this may be the cause for this better values in longitudinal level. So we tried to, sorry, what I didn't tell you. Up here you see a time slider. So every dot represents one date where we have measurements from our measurement train. So you can also slide back in time and forth to compare and to see what is actually happening. And at this point, we have a very important factor. We also had it in the discussions yesterday, humans. Because whatever tools we build and whatever models we use, we have to make sure that our humans, our users, they trust our data and our models and our tools. Because if they don't trust our tools, then you can spend a lot of effort and waste millions. Doesn't matter. So in case of this application, how do we create trust? Very easy. So if somebody clicks on a specific track, he'll get 2 links. And with deep linking, those 2 links will take him to the old application where he can actually see the raw data coming from the measurement trains. So you also have the driver's view, and he can also see the old charts we generated, which will also be provided throughout the next years. So this is a very easy measure to generate trust with the user, because he can always compare the new view of the data with the legacy system and see that it's the same data, basically. Here this is also something we're generating timelines throughout 20 years, because we have 20 years of reliable data, so that we can see what is actually happening in the system. So the next step, and this is the step we are currently working on, is predictions. Trying to answer the right questions is not so easy, because you really have to look at the users and see what they actually want or what they need for their work. So this is something we implemented last month. So now the timeline has been extended into the future. So we have the part with prognosis, where you can also see 3 or 4 years into the future. So if you zoom in somewhere, and you push the slider, you will see how the changes are going to affect the system. We've used very advanced algorithmic methods called linear regression here. So this is just the first part, just to keep it running and to make sure the users gain confidence. But the linear regression part is going to be dropped out quite soon. Because that's not how the tracks degrade, actually. But just to give our users a feeling about what's going on. And then we thought about, this may not even be the right question that the user asks, but maybe he's not interested in what is the state of our track in 2025. But the right question that the user asks is, how much time do I have before I need to set a maintenance measure? And that's why we came up with an additional box here. So you can say you want the prognosis to see how many years do I have until I have to set a measure because I reach a threshold. So if you put this here, so you'll get a new scale. So it will go from 0 years, 1 year, 2 years, 3 years, and 9 years. So don't care. And also this information is provided to help our users to find the right decisions. So regarding predictions, so the linear regression part is going to be dropped quite soon. What we are looking for is physics-based models, because it's quite clear what is actually happening with the tracks. But also we want explainable models, because we want to be able to give explanations about why we believe it's going to change the way we are foreseeing here. And one thing that is also giving us a lot of work for the future is we're trying to show what cause and effects are. And if you look at the cross-section here on the right, you see this is a local phenomenon where you have mud pumping on a very short stretch, which is giving us headaches sometimes. And you see here the number of factors that is the cause for this effect. Yeah? And of course, our measurement trains and the other data sources we show just give us some hints about what is going on. So this is why we need more data, but we need the right data. And this is also key, I think, not just going big, but also trying to keep it as simple and as small as we need to get the right data that we need for the prediction. So what we are looking at is we are very good at the conditional, at seeing the condition of the tracks, but we are not very good at looking at the loads and seeing all the other effects. So currently we're just implementing some ingests for real-time data from our train operations. I'll possibly, within the next half year, get additional data from around 200 locomotives that travel our network, where we get some measurements from the sensors regarding slip, tractive force. 1 minute, yeah, thanks. Then hydrogeological data to being able to model subsoil conditions, meteorological data, and additionally generated parameters that we can generate from the LiDAR scanners, for example. And IoT sensors, like in our switches, we have a lot of IoT sensors. So summary, it takes a long breath, especially in a like traditional field like railways to keep things moving and to implement the things we've done. Tidy data is essential. That is something we've neglected for the last 20 to 30 years, I think. It's very important to have a common layer, else it's not going to work. I think one thing is to use flexible tools that are scalable and probably open source tools. I'm really a fan of that. Keeping big data as small as possible. This is also related to the resources problem we heard earlier. We want to keep our CO2 footprint small. And for us as a team, it's very important to be independent in the further development of the tools. So that's also something we had in mind when we did that. And we need experts with a thorough understanding of both engineering and data science methods. I think this is also key. Yeah, trust. So just last slide, challenges. We heard it yesterday in the discussions, data ownership. Maybe with our data, it's not so complicated because a lot of data is generated on our own, but we have it with our switch operators and switch companies. There's also something to discuss, open source and in-house knowledge versus vendor lock-in, collaboration within our sector versus everybody is on their own. It's also something we discussed yesterday evening. Does it make sense to combine resources and to share knowledge? Yeah, trust from our users, human in the loop is very important when we generate models. And one thing I see coming is the whole liability and responsibility issue, because suddenly my data scientists in the team are responsible for something which is not their base domain. So this is also interesting. And one thing that is hard for me, focusing on specific questions. We see a lot of potential in our data, and it's really hard to keep the focus and like finish one thing first and push it into production before you start on another thing. So I think intelligent maintenance for me means that the decisions should be made by humans, so by our track managers, track inspectors, and we want to support them by the right data and tools. And I hope this gives some input for the coming discussion. Thank you.